I was asked to give a talk about catalysis in space. I'm a chemist by training. So what kinds of catalysis might we get? He said precisely what's written there. A catalyst is a substance that accelerates the rate of a chemical reaction. I've just spoken at the Third Nanospace Joint Conference, and I had about catalysis in space, and I had a really good time, as I normally have if you actually know me. It's something that I think we're now at a stage in astrochemistry that we can go beyond just simple gas phase chemistry, simple solid state chemistry involving ices and radicals and light and cosmic rays, etc., and start to think, what other chemical processes can play a really significant role? And as chemists, we're taught a lot about catalysis. We're taught how catalysis can accelerate chemical processes. There's a lot of organic chemistry that's accelerated by the presence of acids and bases. We don't account for that yet in any of the models in astrochemistry. We should be accounting for it. In fact, probably we don't need to do that many more experiments, because people have been looking at this in physical organic chemistry for decades. We know how it works. We know the kinetics. The only twist that we might have to include now is how do we measure kinetics in ices that are acid-base catalyzed? Beyond acids and bases, it's probably time to plunder the transition metal inventory of catalysis. We all know how important industrially transition metal catalysis actually is. And it's fortuitous that the most abundant metals in space are those that we use in terrestrial transition metal catalysis. So I urge colleagues to go back to their undergraduate chemistry, if their background is in chemistry, and look to transition metal or organometallic catalysis, both molecular, looking at single atoms surrounded by reactive ligands, and clusters, because we potentially, in the environments we see in space, can have both types of catalyst. Single atoms deposited on the surfaces from the gas phase, small clusters, a few tens of nanometers across, generated in silicate minerals by interaction with cosmic rays in a reducing, a hydrogen-rich environment. There's a lot of chemistry out there. There's a lot of good catalyst chemists out there working in these fields. And maybe they shouldn't be dismissive of doing astrochemistry. It might not be a high pressure, high temperature industrial environment trying to get turnover to tweak the catalyst to get the next fraction of a % of efficiency. It's more about, can some of these catalytic reactions help us explain the complexity of chemistry that we can generate in astrophysical and planetary environments that might enable chemistry to evolve into life and biology.